Welcome everyone. In this video lecture, we will solve a GATE 2014 question which is based on the double diode based clipper problem with two additional DC supply voltage. So the question is two silicon diodes with a forward voltage drop of zero point 0.7 volt are used in the circuit. So two silicon diodes are there, D1 and D2, which are in the forward voltage drop having zero point 0.7 volt. So that is our cut-in voltage across the silicon diode is zero point 0.7 volt. We have to find the range of input voltage Vi for which the output voltage will be same as that of input. Okay, so the output voltage same as that of input we have to decide. So the options are the Vi value range in between minus 0.3 volt to 1.3 volt, Vi value range minus 0.3 volt to 2 volt, minus 1 to 2 volt Vi range, and the Vi range minus 1.7 volt to 2.7 volt, and the input voltage is given as sinusoidal input signal. Okay, so this one is a sinusoidal input signal is given, and this one is circuit. So here we can clearly see there is a resistance, two diodes, two additional supply voltages are there. So this one is basically a clipper circuit. So this one is a clipper circuit with two additional DC supply sources. So first of all, we have to modify this circuit as a simple ideal diode based clipper circuit. So what we have to do, first I am drawing the same circuit here. So I am just placing the same circuit here. Okay, then after the same circuit is there. Okay, the same circuit. Now after that, this supply DC voltage supply can be, because here minus 1 volt, so the better way to make this DC supply as, okay, I am just writing as a minus and plus, and I am writing 1 volt. This minus 1 volt will be 1 volt, but this polarity will be changed to minus and plus. This is a simple fundamental rule of conversion of this DC supply voltages. Okay, how to convert means if this were minus 1 volt or minus 2 volt, we have to just reverse it. So now this one is the thing. We have reversed the this voltage to this. Okay, now and this one is okay, because this one is plus or minus 2 volts, so no need to change. Okay, then after what we are doing, again we have to modify the circuit. Now the circuit is more or less, we have changed this one, and we have removing the silicon diode. Okay, so that's why we have to put a additional voltage one, that is our 0.7 volt, and this one is now minus and plus. So this one is basically 1 volt supply. Similarly, this silicon diode, again we have to remove this one with a plus and minus. Okay, this one is our 0.7 volt. We are just replacing the silicon diode cut-in voltage, so minus and plus. If some diode is there and this one is silicon, so we have to just remove it, this minus plus 0.7 volt, and this one is a ideal diode, say D1 ideal diode. Okay, the same thing we are doing here, and we are just replacing with 2 volt battery. Okay, so this one is the circuit. Okay, once again one can also modify this as the final form. We can make like this silicon, we can remove this silicon and this voltage. So this one is 0.7 volt, 1 volt, so there must be some voltage having minus terminal, plus terminal. Okay, and this should be our 1.7 volt, and here it should be plus terminal, minus terminal, okay, and it is 2.7 volt. Okay, we have just replaced this one, okay, as a 2.7 volt, and this one as a 1.7 volt battery. That's why this one 1.7 and this one is minus 2, so 2.7 volt. Okay, 2.7 volt is there. So this one is the modified circuit. So now this simple problem can be viewed as a two diode based problem. So if we take, or in such situation, better to divide this problem. In such situation we have to divide this problem in two diode problem. So for that purpose, what I am doing, there is a resistance, okay, I am making, okay, then after there is a diode, okay, and I am saying this voltage is say V1, T1, 1.7 volt, R, and some sinusoidal signal. Here we are giving sinusoidal signal Vi, and we are taking the output. So this one is one situation, and the other situation, in the other situation, what we can do, one, then this one is the other thing, 2.7 volt, this one is our D2, R. In such situation better to break into problem. Okay, part 1, this one can be part 1, and another one that involves this one. Okay, so this one and this one, two diodes based two diode based problem is subdivided into single diode problem. And now we have to find the output response of each one, and both the value of V naught 1 and V naught 2 will be, the common part will be the output voltage V output. Common V naught 1 and V naught 2 be the output voltage, because both are in parallel, so the common V naught 1 and V naught 2 will be the output. So now we have to go for the simple process to find out the V naught 1 and V naught 2. So in this case, say this one is our case 1. I just, and case 2. And just showing the steps how to deal with such type of problem. In my earlier video, I have already solved this type of problem in the very beginning. So now in such situation, we have to go for step 1. So in step 1, what we have to do, we have to find the transition voltage, transition voltage, where the diode D1, here D1 is just on, and at that time, at that time, the current in the circuit, in the circuit will be 0. Okay, so for the transition voltage case, what I have written, this one is the thing, and diode is just on, so I'm just making this one is on, and this one is the voltage, plus minus V1 R, and plus minus Vi. So when the diode is just on, and if we apply Kirchhoff's voltage law, keeping this I equals to 0 in the circuit, it will give Vi, and this one is 1.7 volt minus plus 1.7 volt equals to 0. So it is giving a minus 1.7 volt Vi. So this Vi is our transition voltage. So why we are finding this transition voltage? Because if we know the transition voltage, this one is the input wave, okay, and then the transition voltage is Vi equals to minus 1.7. So this one is a line parallel to the time axis, that is our Vi equals to minus 1.7. Now above this line diode is either on or off, or below this line diode is either on or off. So if we are telling above this point 0.7 volt, or it may be suppose 5 volt here, we are assuming some 5 volt, so diode will be in the off condition, because diode direction is more or less like that, okay. So above this line this will be positive, so D1 will be in the off state. Okay, in my earlier video it is already mentioned how to think. So D1 will be off when the input is above minus 1.7. So any point, suppose 5 volt or 0 volt. So if this one is 0 volt, this one will be reverse 0 volt. This one will be off condition, because here it is more positive. Okay, negative. This one is negative and 0. So this one will be in reverse by, and below minus 1.7. Okay, so if this one is more negative, then it will be in forward by, so D1 become on in this case. So this one is very important situation. So now what we have to think, when D1 is on, so the output voltage will be if you apply Kirchhoff's voltage law in this loop, the output voltage will be V01, okay, V01 plus V01 I am writing, plus 1.7 equals to 0. So V01 equals to 1.7 voltage when the diode is on. So when the diode is on, it is 0.17 volt. So this one is the on condition. Okay, so this one is the output. So I'm taking some different color. Okay, this one is the output. Okay, and when D1 is off, when D1 is off, when D1 is off, the circuit will be like this. Okay, so this one input will be same as that of output 1. Okay, during D1 is off, so D1 is off in this interval, so D1 is off, so Vi is nothing but simply V01. So the output response will be more or less like this one. So okay, so this one is the output, that is our V01, because when D is off it will be same, okay, and when D in on below this line it will give a constant value. Okay, so this one is one output V01. Similarly, in this case, what we have to find the transition voltage. So I am saying a step 1 transition voltage, so it will be on, okay, and this current will be 0. So we have to write plus Vi minus 2.7 volt equals to 0. So Vi is equal to 2.7 volt. Then after again we have to write, we have to draw the input voltage. Okay, then a line vi equals to 2.7 is more or less, we can say this one. Now we have to decide above this line diode D2 is on or off. Okay, so now here we can see that above this line, above 2.7, if any value above 2.7, diode will be, D2 will be on, above 2.7 volts, so D2 will be on. Suppose 4 volts, so it will be on. Okay, and below 2.7, any voltage like 1 volt, so it will be reverse bias, so D2 will be in off condition. So this one is very vital. If you know this thing, so it is very easy. So now when D2 on, D2 on, so if we apply Kirchhoff's voltage law in this section, in loop 1, say V naught 2 minus 2.7 volt equals to 0. So V naught 2 equals to 2.7 volt. So output voltage is 2.7 volt when D2 is on. So D2 is on above this line, above this line. Okay, clear? And when D2 is off, when D2 off, then V naught 2 is same as that of V in, because the circuit will be open circuited and there will be some voltage, that is our this, so there is no need to worry about this voltage. And this one is V naught and some Vi, so V naught 2 is nothing but simply same as that of voltage when D2 off. So D2 off condition will be below this line, so if this one will be constant, then this one will follow the same. Okay, okay, clear? So now we have to take the common part in between these two graphs. In these two graphs we have to take the common link. So the common link, if we plot one, this one is the input. Okay, so now for this one, due to v1 v naught 1, I am saying this one is v naught 1, so v naught 1 will be more or less this one, say v naught 1. Now for v naught 2, for this one I am saying this one as a v naught 2. So for v naught 2, it go like this, it go like this, and it should be constant, it will be overload, and then it will go like that. Okay, and for this one, so we have to take the common portion of the output response. The common will be this one and this one, and the value, this point will be our how much, 2.7 volt. Okay, so this point will be our 2.7 volt, and this point will be minus 1.7 volt. Okay, this one is minus 1.7. Okay, so the voltage for the both the v naught equals to vi, so in this case v naught equals to vi will be appear. So vi value range will be in between minus 1.7 to 2.7 volt. Okay, so in that way we can identify how to say the output response and in which interval the v naught equals to vi for minus 1.7 to 2.7. So the actual response of this output will be like this one. Okay, and this value will be 2.7 volt and this is 1.7 volt. Okay, and for this region only v naught equals to vi work. Okay, so this one is the answer. So we have to identify the correct option for this problem. So the option will be minus 1.7 to 2. So the option is D. So this is all about this question. So in this one we have to first change this one. Okay. Then after we have to just make like this, and then ideal diode based problem. Okay, with replacing silicon diode with 0.7 volt. Okay, then we have divided into two diode based problem. Okay, then after two diode based problem, then after transition voltage, above that transition voltage in this minus 1.7. Above that we have to find diode is on or off. Very carefully we have to think. Then we have to draw the output response. So output response will be this one. Okay, this one. So this one, and in the second case the output response will be this one. Okay, then the common portion we have to take care. So the common portion will be, this portion, the yellow portion. The common portion will be the output, yellow word. Okay, so which region will be the common? This one, minus 2.7 volt. So the answer will be minus 1.7 volt to 2.7 volt. So this is all about this question. So thank you for watching this video.